So in this lecture, we're going to be talking about aldol reactions. Now, aldol reactions are when enolates attack ketones. Alrighty, so we're going to be looking at first just a basic aldol reaction, and then we're going to be looking at, okay, let's go one step further and do what's called an aldol condensation. Alrighty, so we're going to notice that for these reactions, they're going to be base catalyzed. It's the most favorable way to get these aldol reactions to occur is make the enolate through basic conditions. The reason for this, and we'll see, we're going to use aqueous sodium hydroxide and water. What you're going to notice is we're first going to form an enolate, then that enolate is going to attack another ketone of itself, or you can mix it up and get a little different. And then we're going to form some product where we're then going to have to protonate. And we're going to see why acid catalyzed isn't really the way we want to go with this. So the first step is, and I'm going to go this way before we predict a product, is, okay, NaOH is going to come in and steal a little proton, make a pi bond, kick electrons up. All right, if we did this acid catalyzed, you're going to have to go through all this trouble to make just an enol. It's not going to be strong enough of a nucleophile to attack this electrophile, which is going to be another one of itself. Now, this might be the first time you're seeing an attack like this. We're attacking a molecule of ourselves. That's what we're doing here. So with the enol, it could be possible maybe, but with this, notice the strong negative charge that we're going to use arrow pushing with. We're going to push electrons down, and then we're going to attack the carbonyl, which has a slight positive charge. All right, because of induction from the pi electrons, we're going to kick electrons right back up. Alrighty, so we're going to have a reformed carbonyl. We're going to go to this carbon here, and then we're going to attach like this. So notice now we have a tertiary oxide group here, and it can't just come back down and kick everything off. That's too unfavorable to happen, right? It could maybe kick things off, reform pi electrons here, reform the enolate maybe. It's just not very likely, right? We had a strong nucleophile attack here, and we made a more stable intermediate. So instead of just coming back off reforming carbonyl and kicking everything out, we're going to notice that it's just going to protonate itself. And to do this, well, if we're under basic conditions, we know that if we are using NaOH, has that negative charge, well, then we can just take the conjugate base of that exists in solution, swimming around somewhere, water, and simply reform base. So what we end up getting is a beta-hydroxy ketone. Beta, alpha, beta, beta-hydroxy ketone. That's what we call the product of just an aldol. So I'm going to write that out here, a beta-hydroxy ketone. So that's just a plain old aldol. You'll find this with many different types of aldol reactions. Now, I want to make an important point before we get into what's called the condensation of aldols. I'm going to go ahead and erase this, so if you need to take any notes, please do. But what if instead of just using acetone, for example, I instead decided I'm going to use acetone and a corresponding aldehyde? All right, what if I do this instead? What happens there? What am I going to get? Well, you'll still get a beta-hydroxy ketone, but you're going to get a mix of products. This is what we call a mixed aldol, when you have two different ketones. You could use a crazy ketone here and another crazy ketone. We're actually going to see, hopefully I'll bring up an example in the practice problems where we have a mixed aldol and we're asked to predict the products. But if you have, for example, these two, which I just kept really simple just so you can see it, we're going to get a mix, okay? So for the first one, let's say this is going to be our enolate nucleophile, right? Well, we'll say that, okay, we'll make the enolate. and I won't draw the mechanisms, but hopefully you follow. All right, so now the acetone is the electrophile. Okay. And just to prove a point, I'm going to try and be really, really thorough about this. And then we get protonation, which I won't even draw. Okay, so following that process we just looked at, we're going to use this aldehyde that was kind of like, oh, we just chopped off a carbon of the acetone molecule, and then we form this. Okay, but notice what happens if instead we make acetone the enolate nucleophile. And instead we attack our aldehyde. Now notice something kind of interesting here. So instead of, and of course I forgot to add here, we're going to get protonation, same with the water molecule that NaOH made. So notice the difference here between these two. They look very similar, but they are very different, right? And you're going to get a product mix in your reaction mixture because you used an unsymmetrical ketone mix, right? If I used just this, it would be fine. I would get one product, but since I'm mixing acetone with this ketone here, or sorry, not the ketone, this aldehyde here, well, we're going to get a mix, right? We're going to get one of this one where we have a aldehyde ketone, still beta-hydroxy, but it's a beta-hydroxy aldehyde, whereas here we have a beta-hydroxy ketone. It's a little different. Okay, so hopefully that idea makes sense of the mixing that you can get. So remember we said aldols are just making an enolate nucleophile of one ketone and it attacks another of itself, but we can also mix it here. You should be expected, if you're given a product mix, to show every single possible product that you could get. Okay, so now that we've established that, there's another extension of this idea, which says, okay, if I have, let's say acetone, I react it with sodium hydroxide and water. All right, I'm going to get this here. What happens now if I heat this? If I add heat, what do you think is going to happen? Well, given that we have a strong base and we're heating it, what do you think is going to maybe happen to this OH group here? Well, it's going to want to leave. So that's exactly what happens. And what we're going to notice is we're going to get an alpha-beta unsaturated ketone, which is basically alpha to beta, there's a double bond. That's what that means, alpha-beta unsaturated. Right? So this is what's called an aldol condensation. We take a ketone, we're going to do an aldol reaction with it, we're going to make it join with another one, but then that OH group, we're going to heat it, stress it, and it's going to leave, because if we're under basic conditions and we're heating something, this is okay to leave. It doesn't need to be protonated or anything because it's in a basic medium, okay? So it just leaves. And we get that alkene. So hopefully that's quite simple, and it would do this through simple E2 elimination. NaOH would be like, come in, attack this, pi bond, kick out. Just simple E2 that you've learned. Okay, so that's what we call an aldol condensation. Now I want to look at what's called intramolecular aldol reactions. So this is kind of just a brief little point here, but it's very important that you know what happens when you heat an alpha beta hydroxy ketone. This will actually come up again in the Michael reaction. We're going to see that this is subject to attack by some of the weak, I believe they're called Michael acceptors. I always get them switched in my head, but because they don't really make sense the way that they're put. But anyways, that's aldol condensations. Now I want to talk about intramolecular aldols. Let's say, for example, you had this molecule, all right, an aldehyde ketone, right? You could probably give it a name, but I don't want to because we don't got time for that. Let's use sodium hydroxide and then water, and let's determine our products here. Now, we know that life wants to move towards less complexity. Now, do you think that we're going to get big branches where this molecule is going to attack another molecule of itself and make this crazy big chain, and then maybe it polymerizes together and make huge molecules? Well, probably not, because life, remember, entropy wants to move towards more disorders. So if we are going to get a reaction to happen, it's probably only going to happen within itself here because of how big the molecule is already. Now, there's something important to notice. It wouldn't do this. It would attack another molecule of itself, if at all, if we only had one ketone group. But notice we have two here. And what's going to happen is, well, since we have two ketones, it's going to just attack itself. It's really interesting how this happens. So let's draw a mechanism here. Let's say the aldehyde will make a ketone. An enolate. So let's have our hydrogen here. And our NaOH is going to attack the hydrogen, form a double bond, and we're going to push electrons back up. Okay, so notice here, we made an enolate, and then we have a ketone. So what happens here is it's like, oh, well, I don't really want to have a negative charge. I'll give it to my dear neighbor here. And he's going to attack the carbonyl intramolecularly. Now, to determine how big your ring is going to be, count the carbons and make the corresponding ring. So we have 1 carbon, 2, 3, 4. So this is a 4-membered ring. Maybe I should have used a different example here, but you know, it's life. Oh geez, this is more cursed than I wanted it to be. Anywho, so let's label this carbon 1. All right, from carbon 1, we're going to have our aldehyde, and then carbon 1 goes to 2, 3, 4. 4 is going to have a methyl and an oxygen with a negative charge. And what happens here is, well, we're just going to see exactly what we got before, which is going to be protonation from the water molecule, conjugate base. All right, and we're going to get our final product here. Where we get and still, you should notice this is an alpha beta unsaturated ketone, but it's just cyclized, right? Whenever we do an intramolecular aldol, when it attacks itself, it makes a ring. So that's an important note to make. But now that we have everything here, we looked at aldols, aldol condensation, mixed aldols, and now intramolecular aldols. We now know everything that there is to know about aldols. Now this is probably your first time seeing this complex of content in organic chemistry, unless maybe you've done organometallics, but this here is probably as complex as it will get in organic chemistry, so don't feel too bad if you're not getting it right away. Maybe try and rewatch the lectures, or I'm going to try and do 5 practice problems so you guys really understand aldol reactions. So without further ado, let's get into our first practice problem. So in this problem, I would like you to determine with this, for this one ketone reacting with itself, what is the aldol product of this? And this should be NaOH with water. Oops. So I'll give you a little bit of time to figure it out. Please pause the video now if you want to try it on your own. If not, I'll get right into the solution. Okay, so we have this, this nice little benzene ring here, and then we have 3 carbons and then an aldehyde. So how does this react with aqueous sodium hydroxide and water? Well, I'll redraw my starting material. And our first step, remember, is going to be enolate formation. So we're going to take NaOH, and we're going to see there's a little hydrogen here. next to the ketone in the alpha position, right? Alpha chemistry, that's the whole point of this chapter, attacking the alpha carbon's hydrogen. So we're going to attack that, and we're going to make a pi bond, and we're going to kick electrons up. Okay, this is going to give us this following product. Sorry, I have the allergies today. It's quite fun. But now notice we have the enolate. I want you to see the enolate here in the Aldol reaction as just a bullet. It is just boom, ready to attack. So what's going to happen is we cock the pistol and we're pointing it at some sort of ketone. We're going to shoot it off. Right, that's going to be the folding in of electrons. So it's going to go boom, push electrons in, and we're going to find that we attack another molecule of our starting material. Hopefully that idea doesn't surprise you. So the bullet goes off, and the bullet, I should say, goes off, and we make, we're going to attack this ketone of the same species. So let me draw my product here. I'll draw it in black. Why not? So we're going to have, it's good to draw your starting, or the starting enolate exactly how you had it, and then just add on. So here we're going to attach to a carbonyl with the O-, and then we're going to have the rest of the chain. So so we have, we're on this carbon here, then we move over to this carbon, and then our benzene ring. So let's double check our work here. We start at this carbon, we go to this one, and then benzene ring. So this is the protonated form here. So we just need a molecule of water to come in and protonate our oxygen with the negative charge. So let's draw our final product nice and neat here. And every time you do just an aldol, not an aldol condensation, you should always end with an alpha beta unsaturated ketone. So ask yourself, do I have an alpha beta unsaturated ketone? Well, let's see. Here's an alpha carbon. Here's a beta carbon to the ketone. Well, notice beta-hydroxy, not alpha beta unsaturated. You need to have a beta-hydroxy ketone. Ay caramba. Beta, meaning there's a hydroxy here, ketone. Beta-hydroxy ketone. It would be alpha beta unsaturated ketone if we then heated this, and this would do elimination to form the alpha beta unsaturated ketone, where we'd have a pi bond there. But sorry for misspeaking there, but this here is going to be our product. All right, let's go on to another practice problem. Next is going to be a little bit of a discussion to real-life applications of Aldol reactions. Now, if you remember this simple reaction of glucose to pyruvic acid by glycolysis, maybe from a biology class, maybe you've learned there's intermediate steps with different enzymes. One of these involves fructose 1,6-biphosphate, which is this huge molecule here, and then it goes through this enzyme called aldolase, right? Aldol reactions, it's going to do what's called a retroaldol and turn this product into these two products here, dihydroxyacetone and glyceraldehyde 3-phosphate. Now, notice here, aldol, meaning Aldol reaction, ACE. ACE just means enzyme. So hopefully you remember this from a simple biology class, maybe in college. You've maybe looked at this step, or just overall the whole process of glycolysis. Now I want to talk about how this reaction works. Now it's going to do what's called a retroaldol. We haven't talked about that, but basically it's just an aldol reaction in reverse. It actually happens with most complex products like this. It's just not going to want to form the aldols, and it's going to do the reverse. Now, that's what happens here. Think about this process, this aldol reaction going in reverse. So with this one, imagine making an enolate here and then attacking this aldehyde, you get this product. But here what happens is we're going to see there's a alpha, beta, or sorry, not alpha there. Alpha's here, beta's here. This was once, or our product here is a beta-hydroxy ketone. So think about this. If I wanted to do a retro, you just have to do all the steps in reverse. So what happens is these electrons fold in, kicks off this group, makes an enolate. Enolate's going to push electrons down and reform. So basically what this enzyme does is he just splits up this here to form our product there. So this is glyceraldehyde 3-phosphate, this is dihydroxyacetone. So hopefully that idea makes sense. I just wanted to point this out as one of our practice problems because this is where these Aldol reactions come in handy, is in the real world itself. You'll actually see a lot of alpha chemistry in the real life. So yeah, so on to the next discussion / practice problem. So for this problem, I want you to not only predict all the possible products, but also draw the mechanism for just one of those. Okay, so hopefully maybe you've paused the video, maybe tried it on your own. I encourage you to try that approach, but maybe not, but it's all right if you didn't. Let's draw the mechanism for this one's the enolate, this one's the electrophile. So let's see here. So we're going to form an enolate with sodium hydroxide attacking a hydrogen to form an enolate. Okie dokie. Oh, and then I'm going to need a bigger arrow for that, so I tried to draw a small little arrow. Alrighty, so what we're going to see is I'll move here. It's going to push in electrons and attack the carbonyl, push up electrons. So we're going to notice we're going to reform carbonyl. And here we're going to attach to a carbon. That's going to have 1, 2, 3. It's going to have a propyl group to the side. So we have that propyl group. We're going to have a very interesting chain here that there's a name for it, but it's slipping my head, so I won't go ahead and name it. But there should be a name for that functional group, and there should be an oxygen with a negative charge. Okay? The next step here is to just protonate, so we're going to get protonation. And it'd probably be better to draw it like this, right? Where we're going to have water. So I should have elaborated. Water is going to give that proton. So notice here, this will be our aldol product, but we're not done. Okay, we're going to heat it up and we're going to do elimination. It needs to be alpha beta unsaturated. So alpha beta. We're going to steal a hydrogen from this part. So we have NaOH, negative charge, and it's going to attack, form carbonyl, kick out OH. Okay, so that would be our product there, our first product. To think about other products that we might get, so we could have this be the enolate in 2 different separate ways. So let's draw it as if this side was attacked as the enolate. So we'd have it attached to this carbon with an OH and then the rest of our chain. Remember, we'd get some elimination there afterwards, and then we'll have the rest of our chain here. So kind of ugly, but hopefully it gets this idea across. And now we'll put the enolate on this side. So let's draw our starting material, and then we have that carbon that became the enolate. And now we have this group with the OH. And then we eliminate to form double bond. So a little ugly, but we're going to get three major products here. They're all just a little bit different from each other. Hopefully, if you really need to and you can't just see this process of just spontaneously producing them by in your head going through the mechanism, just write out the mechanism. It will take more time, but it will save you from making little mistakes. I may have made a mistake here, maybe with like cutting off a carbon or something, but the idea is the same. You get an alpha beta unsaturated ketone for each of these because we're heating it. It's an aldol condensation, and we could have this be the enolate or two variants of the enolate on this molecule. So that's going to wrap up this practice problem. Let's get to two more of them. So for this problem, I ask you, what two aldol reactants could I put together with aqueous sodium hydroxide and water to form our product here, this? So you're kind of doing a retrosynthesis. This will help you, this exercise is to help you when you're given an a beta-hydroxy ketone, how you can think in reverse to see, okay, what two aldol things will I need? Okay, so I hope that you took the time to maybe figure it out. If not, that's okay. That's why we're here, to learn. Learning's great. This one is a little tricky because it involves an aldehyde maybe you've never seen before. Now, me, myself, I love this little molecule. It's really cool for the study of abiogenesis. Maybe that's a hint if you know what that is. But if you don't, it involves formaldehyde. Now, we weren't asked from a mixture of products. We were told we have just one, and that should be a clue that we should only have one electrophile and one nucleophile attacking the same way. Ooh, I almost dropped my marker. I keep doing that. But we should have an electrophile that can act as a nucleophile and a nucleophile that can attack just one time, or just one time. So notice here, formaldehyde is going to be what this is here. And I'll prove it to you if you can't see it. But our nucleophile is going to look like this. Now, I won't go ahead and name that unless you want to, then go ahead and look it up on MolView or something. But I'm not about that life. So if you can't see that these are our reactants, let me prove it to you by doing an aldol reaction. So we need to identify alpha carbons that are able to do an attack. Now, does formaldehyde have any, and this is formaldehyde, does formaldehyde have any alpha carbons where we can pull off a hydrogen and do one of these reactions? Well, you'd say no, because it's literally just one carbon. That is the carbonyl carbon. That's a lot of carbons, ain't it? But anyways, we have the carbon with the carbonyl and then the two hydrogens. So there's nothing sodium hydroxide can do with formaldehyde. Now, on this molecule, there's one carbon that has alpha hydrogens. Now, notice this alpha carbon has two carbons, two methyl groups, and then this ethyl group coming off of it. And then there's the rest of the chain over to the right. Now, there's no hydrogens here, but there is a hydrogen over here, and because of that, it's the only place where we can rip a hydrogen off. So we have a hydrogen here, hydrogen here, hydrogen here. So what NaOH does is he comes in and he says, okay, I'm hungry. I'm going to take a hydrogen, fold in, make an enolate. Sorry I'm blocking the board. I'll move in just a second here, but notice we're going to form our enolate. Pretty simple. And then it's going to attack formaldehyde. Little itty bitty formaldehyde. Now, I think this is awesome because we see this kind of reactions occur with an abiogenesis, which is the study of a non-living origin. Sorry, I'm yapping because this is what I want to go to grad school for, but it's formaldehyde just continually does these sort of reactions where they polymerize together and make these sugars. Now this is pretty cool. Maybe aldol fits in there somewhere. Kind of just a cool idea. But where enolate's going to attack the electrophilic species of formaldehyde, and we're going to get the following product. And then all we have to do is simply protonate this little product here because he's not happy the way he is. He'll pass it off to, he'll play hot potato with the water. And we get our product. That's exactly what we have here. So keep in mind that your aldol could also be as simple as formaldehyde, right? But this was just to kind of get you to think out of the box here, not only of the simplicity, but how we can think retrosynthetically, right? So if you're given a synthesis problem where you're asked to make a beta-hydroxy ketone, you know how to do it. So let's move on to our final practice problem. So in this problem, we're going to even think more retrosynthetically here. We're going to be given an alpha-beta unsaturated ketone, and we are asked, what was the starting ketone, right? Notice that this is intramolecular because we end with a ring. Okay, so I want to begin by just undoing what we did. So if I have an alpha-beta unsaturated ketone, I know this must have come from a beta-hydroxy ketone. So alpha-beta, we know that there should have been an OH here. All right, so I'm going to start from here. So I'll even go like this to show that we're moving down. So we go from alpha-beta unsaturated ketone to beta-hydroxy ketone. Now what's going to happen is, okay, well, we know that this had to be the enolate site where it attacked our carbonyl, and then it got protonated. So this was initially formed from deep protonation, which was formed from the attack of this carbon here. So we'll call this carbon 1. So carbon 1 here, we have the ketone where it attacked from. Carbon 2, carbon 3, 4, 5, 6. And then it's going to be from here. So does this look to be true? We make the enolate here, we attack from here, we make 1, 2, 3, 4, 5 membered rings. So yes, this is how you want to go through the thought process here, noticing you have an alpha-beta unsaturated ketone, okay? So now let's draw the mechanism for how this occurs overall. Now, you could get a mixture of products, but we're asked to make specifically this one. So what happens first is sodium hydroxide comes in. And form our enolate. Which will then attack sorry, I'm going kind of quick here, but don't want to make this video a million years long. And then water will give up a proton. And then under heat, sodium hydroxide is going to come in and do some elimination. And we're going to get our final product. So hopefully that's not too hard to see. But notice we thought retrosynthetically, and then we just showed the mechanism for how we made this ketone into this product. So I hope that you guys enjoyed this lecture. If you did, please drop a like, comment, and subscribe. I'd greatly appreciate it. And I hope that you have a wonderful day.